right, let's talk about some things the FAA wants you to know as a power plant mechanic about engine operation and maintenance. And let's lead off by talking about airworthiness directives. Now, airworthiness directives are letters the FAA writes to owners or operators of aircraft saying some defect has to be repaired within a certain period of time. Well, the thing you need to know about these is these are federal aviation regulations and they must be complied with unless a specific exemption is granted. So you must comply with airworthiness directives, and airworthiness directives of an emergency nature require immediate compliance upon receipt. So if you have an emergency AD, you must comply with it right away. All right, now let's take a look at the type of question they're going to give you on the FAA written exam about this. They're going to say, all right, super mechanic, let's assume you have a model 0690 engine. By the way, this engine's made up. There's no engine like this in real life. They made it up for the FAA written exam. But you have a model 0690 series engine, serial number 5863-40, and this particular engine has 283 hours time in service. All right, now that's the engine. Let's take that away, and let's take a look at the AD they're going to give you on the test, and they're going to say, this particular AD is a compliance portion of an airworthiness directive, FAA airworthiness directive, and compliance is required as indicated for a Model 690 series engine, serial numbers 101-40 through 5264-40, and an IO 690 series engine, serial numbers 101-48 through serial number 4023-48. You must comply with C within 25 hours time in service after the effective date of this AD, and every 100 hours in time in service thereafter. Now let's move this back down and take a look at the bottom and move the engine back in here, and let's see if we comply with this particular engine. First of all, it's an 0690. Well, here we are, 0690 series engine, so we may have to comply with it right there. You might see that. But we've got a serial number 0690 5863-40. Well, the serial number for this 0690 engine down here was 5264-40 from, it started out, let's take a look at where it started, at 101-40. So if we're at 5863, are we in between, let's take a look at it again, are we in between 101-40 and 5264-40? And the answer is no, we're not in between those, so we probably don't have to worry about that. But hold it, there's an IO engine. Do we have to worry about it if we're an O engine? No, IO we don't have to worry about that, so we don't need to worry about those serial numbers. And so it looks to me we don't have to worry about A. Now let's go down and take a look at the rest of this AD note that they give us here. And we go down and look at B down here, and it says for model 0690. Now that might be us because we are a model 0690. Serial number, and the number in this case is 5265-40 through 6129-40. Let's take a look at the engine again. We might have to comply with that because we are 0690. And we are in between 5265. By the way, ignore the -40. When they build engine 5265, they get done with that, the next engine will be 5266-40. They keep going up, but the -40 stays with each of those engines. But we're at 5863, so we are in between 5265 and 6129, and so we might have to comply. Let's continue. And it says you must comply as follows. All right, we're not an IO, so we don't need to worry about that. Number one says, within 25 hours time in service after the effective date of this AD, and every 100 hours time in service thereafter for engines with more than 275 hours time in service on the date of this AD. Now, let's look one more time at our engine. Did we have more than 275 hours? Son of a gun, we did. We had 283 hours. And by the way, this is the way I would answer this on a test, is I would write this down and keep comparing it. So we did have 283 hours. It looks to me like we are going to have to comply with number one down there within 25 hours time in service. Let's check and see if we have to comply with number two underneath that. Okay, prior to the accumulation of 300 hours total time in service and 100 hours thereafter, every 100 hours time in service thereafter, for engines with 275 hours or less. Now, we don't have to comply with that because if you remember, we have 283 hours, so we don't have to comply with two. Let's take a look at C and see if we need to comply with that. Well, yes, we do, because this is what you do when you comply with it. And it says inspect the oil pump drive shaft, that's part number 67512, on applicable engines in accordance with the instructions contained in the Conan Service Bulletin number 295. We are assuming this happens to be a Conan brand engine. Any shafts which are found to be damaged shall be replaced before further flight. These inspections shall be continued until Conan PN 67512 redesigned or PN 74641 oil pump drive shaft is installed, at which time the inspections may be discontinued. Well, you know about that right now. So what is the answer to this question overall? Do we have to comply? And the answer is yes, we have to comply. Now, we don't have to comply with A because it's outside the range of serial numbers, but we do have to comply with B because it does apply to that range of serial numbers that we're in here. And we have to comply with Part 1 of B because the airplane or the engine does have more than 275 hours time in service. It has 283 hours of time in service. That means we comply within 25 hours. And what do we have to comply with? We have to comply with C down there at the bottom. C, nothing to it. Well, this is obviously too easy for everybody, so let's you and I do another one. This time, they're going to say you have an IVO 355 engine. It's a T8164 serial number. Total time is 2,100 hours. Now, the AD would read something like this. It applies to all IVO 355s. Yeah, we'd have to comply with that. And if it's serial number 8,000 to 8,300 and we're at 8164, would we have to comply? Yeah, we'd have to comply with that. So far, so good. It looks like we are going to have to comply with it. And finally, we have time in service, total time in service, 2,100 hours, and it's from 0. This implies a 0 down here, from 0 to 2,400 hours total time. So would we have to comply? And the answer is yes, we would. Yes, the AD would apply. The type of engine matches. It's an IVO 355. The serial number is within the range, and the total time in service, 2,100 hours, is less than the 2,400 hours specified in the AD. So we would have to comply with it. All right, and engine AD, that's an airworthiness directive, must be specified then, or must be complied with, exactly as specified in the AD. So you're going to have to read right in the AD and see what it tells you to do. Now, the section in the instructions that is FAA approved for continued airworthiness is called the Airworthiness Limitations section. So you'll see a section in here that tells you what you have to do for continued airworthiness, and that's called the Airworthiness Limitations section. Now let's assume as a power plant mechanic you're taking an engine apart and you want to put it back together again. By the way, there is no truth to the rumor that if you take an engine apart and put it back together again enough times that eventually you'll have two of them. That is not a correct thing. That is not a correct rumor. All right, let's assume you're trying to put this engine back together and you're just getting ready to slap on those magnetos to that engine. You think, wait a minute, hold it. I need to check, are these the correct magnetos? How do you find out the authorized components for an engine for which it's certificated? How do you find out if you're doing the right thing? Well, there's two places you could check. You could check the aircraft engine specifications, or you could check the type certificate data sheets. How do you know which to check? Well, if the engine was designed under the rules of the Civil Air Regulations before 1958, then you'd check the aircraft engine specifications. If, on the other hand, the engine was designed 1958 and on, it would be subject to the FAA rules that came in 1958, and then you look at the type certificate data sheets. So the question you have to ask yourself is, when was this engine designed? If it's been since 1958 and since, you look at the type certificate data sheets. If it's an oldie, then you look at the aircraft engine specifications. Now they're going to ask you a specific question about this, and it's going to go like this. Let's assume that you have a DC-3, and on that DC-3 installed is a R1830-92 engine. Now, where would you find the type design information for that particular engine when it's installed on a DC-3? And the question is, would you go to the aircraft specifications or would you go to the type certificate data sheets? And you would go to the aircraft engine specifications because DC-3s, as you know, were type certificated before 1958. And you can tell by looking at this, this is one of those older aircraft. All right, now airworthiness standards for the issue of type certificates for small airplanes with less than 10 passenger seats in the normal utility and aerobatic categories may be found in the Federal Aviation Regulations, where Part 23. So they want you to know that airworthiness standards for type certificates for small airplanes with less than 10 passenger seats, you'd find that information in Federal Aviation Regulations Part 23. That's where you're going to go to look for that. All right, what is the publication to use to determine whether a power plant repair is major or minor? Well, once again, would you guess you go to the Federal Aviation Regulations? Well, if you guessed that, you're right, because you'd go to Part 43. Appendix A tells you whether a repair is major or minor. Now, let's take a look at another one. Aircraft specification type certificate data sheets are used to find an approved alternate replacement of units not available for replacement. For instance, let's assume, let's take a look at an example. You have a Cessna 180 aircraft that has a Macaulay propeller, and the number on that propeller, for instance, is 2A34C90/90A. Now let's assume that you cannot find that. What are you going to do? And it's been, by the way, it's been severely damaged in a ground accident. Now, if this model is not available, what you do is you go to the aircraft specifications type certificate data sheets, and it would list the alternate propellers that would be available. See, nothing to it. Who determines these things? Well, the manufacturer's maintenance manual, when it's FAA approved, contains approved data for performing a major repair to an aircraft engine. So where do you look to find out what do you do to repair an engine? The manufacturer's maintenance manual, because it'll be FAA approved, because otherwise you wouldn't be flying around in an airplane with it. So it's the manufacturer that determines a lot of these things. All right, where would you find, they're going to say Super Mechanic, a minimum checklist for a 100-hour inspection? And where would you find that information? Well, once again, here you're going to look at the Federal Aviation Regulation Part 43. It's the minimum I'm saying, checklist for a 100-hour inspection. What can a certificated mechanic with an inspection authorization do? That's the question they're going to ask you. Well, the answer is they can inspect and approve an engine for major repair for return to service. So if you want to have an inspection and approval for a major repair, you'd have to have an IA, inspection authorization. All right, now on an R985-22 engine, what they're going to ask you on the test what in Sam Hill they're going to ask you on the test does the 985 stand for? Well, the R tells you it's a radial engine, and what's the 985 stand for? Cubic inches. That's how many cubic inches the total displacement of the engine is. Dash 22 we don't need to worry about, because the Dash 22, some kind of manufacturer's designation of how that engine is configured for the particular airframe. And so all they ask you on a test is what's the 985 stand for? Well, that's the total displacement in cubic inches. All right, now let's assume you do make a major repair in an aircraft engine. Where would you make entries? Well, you'd make entries in the aircraft maintenance records, but you would also fill out a Form 337. When do you have to fill out an FAA Form 337? Anytime you make a major repair or alteration. What's a major repair? Well, a major repair is one that, if it's not done properly, might affect the way the airplane flies, might affect its strength or performance, and therefore it's a major repair, and you'd have to fill out that Form 337. Now let's take a look at engine instruments for just a second. When you do look at engine instruments, occasionally you'll see some green markings and yellow markings and red lines. And they're going to ask you on the test, what do all those have to do with? Well, those are called power plant instrument range markings. And what they do is they show whether the current state of the power plant operation, how you're operating the engine, they show whether it's normal, accepted for a limited time, or unauthorized. Then normal is usually shown as green marking, acceptable for a limited time would be yellow, and unauthorized would be red. Now, occasionally you see something different, something I've never seen, by the way, as a pilot, and I've asked other pilots, they haven't seen it. But the FAA says occasionally you can see a red triangle or a dot or a diamond mark, and they say, all right, super mechanic, what's that mean? Well, that indicates the maximum limit for high transients, such as starting. In other words, sometimes the ITT on a jet engine goes real high during start, higher than would otherwise be acceptable. That's called a transient, and that might be allowable up to a red triangle, dot, or diamond mark, and they want you to know about that. All right, now sometimes they want you to know also that the engine could do more. You could put more power out of this engine than these markings will allow, and they're going to say, why is that? And the reason is sometimes the airframe can't take all the power or thrust the engine can put out. So they're going to say that it's based on installed engine operating limits, which may not be exceeded, but that's not necessarily equal to the limits shown on the engine type certificate data sheets. The engine might be able to do more, but we're not going to let it do more because the power plant or the airframe itself might be a limitation. All right, now let's take a look at instrument discrepancies. You're a mechanic and you have these instrument discrepancies. Would you be able to operate this instrument with these kind of problems, or would you have to replace it? Well, it would require replacement if you had a pointer loose or glass cracked or the instrument was fogged or it would not zero out. For those things, you'd have to replace the instrument. Now, what's an example of a thing in which you would not have to replace the instrument? Well, an example of things in which you would not have to replace the instrument might be, and these are correctable things, a red line missing. Why wouldn't you have to replace the instrument? Because you can put a new red line there. Mounting screws loose. Well, you could tighten them up, I suppose. Leaking at a beeline nut. Well, that would be a plastic vacuum line. Just tighten it up. Or a case paint would be chipped. Well, that's cosmetic. You wouldn't need to worry about that. So if they say the case paint is chipped on an instrument, wouldn't require immediate action since it's cosmetic only. Now, they're going to ask you about engine oil temperature gauges. What do they indicate? Well, if you take a look at an engine oil temperature gauge, the engine oil temperature gauge indicates the temperature of the oil entering the engine after it's been cooled down, not the oil coming from the engine. It indicates the temperature of the oil entering the engine. All right, now, they're going to ask you about construction and design of various type gauges, and they're going to say instruments that provide readings of pressure of about 10 psi, such as pressure gauges and oil pressure, are usually of the Borden type. And here is a Borden type gauge. And the way a Borden type gauge works, by the way, is you have a pressure inside this tube, which has kind of an elliptical shape. And when the pressure increases, the elliptical shape of the tube wants to become circular instead of elliptical, and that wants to straighten out the tube, and you measure the rate at which the tube straightens out on a dial, and it tells you the pressure. Kind of a very, sometimes in aviation you come through and you think, golly, the guy that came ahead of me was a pretty smart fella. And I think this is the case where somebody smart must have been ahead of us here. And that's called a Borden tube, and it indicates pressure. You can also use this to indicate temperature, by the way. And the way you do that is you just put a very volatile fluid in here, and when the temperature increases, the pressure increases, and once again, it tends to straighten out this tube. So you can indicate pressure or temperature, but oil pressure gauges tend to be the Borden type, and if you have more than 10 psi, the FAA wants you to know, you'd probably use a Borden type gauge. A Borden type gauge works very well when you're measuring positive pressures, but some kinds of gauges have to measure very low pressures or even negative pressures. For instance, a manifold pressure gauge actually measures negative pressures. Here's why. The standard pressure on a standard day at sea level is 29.92, but if you have a manifold pressure gauge that's reading, we'll say, around 17 inches of manifold pressure, it's actually measuring a negative pressure because that's quite a bit less than 29.92. Well, a Borden gauge wouldn't work for that. You need something that can both contract and expand, and that would be either a diaphragm or bellows type of gauge, and that's what you use when you have to measure either negative or very low pressures. Now, another question they're going to ask you on a test is, how do oil temperature gauges commonly work? Well, the answer is oil temperature gauges normally work under a principle that says that if you change the temperature of a resistor, the resistance value of that resistor will change, and more or less electricity will flow through it. And therefore, you can use resistance, the changing resistance due to changing temperature, and you can somehow display that. Now, there's two methods to display the changing temperature, and one of those methods is what is known as a Wheatstone bridge. And it takes that changing resistance and measures the change in current, displays that. And another was a ratiometer circuit, which actually does the same thing. It takes changing resistance and sends the current each direction. One direction gets more current, and electromagnet moves the gauge over. So all you need to know for this is that a Wheatstone bridge and a ratiometer circuit are common ways of indicating oil temperature, and they do it by measuring changing resistance, and the result is the indication on the gauge. Of course, another kind of gauge they're going to ask you about is a manifold pressure gauge. They're going to say, all right, what does a manifold pressure gauge measure? And the answer is it actually measures the absolute air pressure in the intake manifold. Whatever the air pressure is at that time, absolutely measures that. Now, let's assume you have a break in the line between the gauge and the intake manifold of the engine and a manifold pressure gauge. What's going to happen? Well, they want you to know the induction system will be, the gauge will measure atmospheric or ambient pressure, just outside air pressure. It might be 28 or 29 inches of pressure, but it's going to measure ambient pressure if you have a line, because it tells you whatever the pressure is, and if you have ambient air getting in there, it's going to measure that. That's what it tells you. Now, let's talk about tachometers. And the FAA wants you to know a tachometer, of course, which measures RPM, is a primary engine instrument, meaning you have to have it. How do electric tachometers work? Well, they're using what it's called synchronous, I should say that right, synchronous motors. And what you have is on the engine, you have an AC generator that puts out an AC frequency, and the indicator will have an AC motor, and those are called synchronous. I have a hard time saying synchronous motors. And the way it works is that as the generator turns, the motor that is associated with the gauge turns in exact synchronization with it, so they both turn together. And basically the indicator here is responsive to the frequency, because the synchronous generator, the AC, it's actually an AC three-phase generator, is putting out pulses of electricity, and it's the frequency of those pulses that determines exactly how fast the motor turns. So they're basically responsive to frequency. So the Synchronous tachometer system is responsive to frequency. Now, where do you use synchronous tachometers? Well, in any engine, and a helicopter, for instance, has more than one synchronous tachometer, at least two. Why does a helicopter have two? Well, one indicates engine RPM, and the other indicates main rotor RPM. So helicopters require two synchronous tachometer systems. All right, now let's talk about temperature indicating systems again. And we mentioned earlier a thermocouple type system. And the advantage of a thermocouple type system is that it requires no power source. Thermocouples, by the way, are used for no electrical power source. So if the electrical system fails in this airplane, you still have this gauge working properly. Now, the way a thermocouple system works is you have two junctions of dissimilar metals. You'll have a hot junction and a cold junction. The hot junction will be located on whatever you want to measure. The cylinder head temperature will be located right on the cylinder. The exhaust gas temperature located right somewhere in the exhaust system. And then the reference indicator will be located generally near the gauge somewhere, the reference junction, I should say. Then the gauge measures the current generated by the difference in these two junctions, the difference in the temperature of these two junctions, and the gauge that measures that current is called a galvanometer. So the things they want you to know about a thermocouple type system is it needs no outside source of electrical power. These junctions create their own electrical power. And cylinder head temperatures, very common, are measured by an indicator and a thermocouple sensing device. And so it's a thermocouple that is used normally to indicate cylinder head temperatures. And they're going to ask you, what is the basic meter used in this system? Well, a galvanometer is a meter that measures very low amounts of current. So the basic meter is a galvanometer. So here's a case where you have exhaust gas temperature. You would have two galvanometers right there. All right, the indication of temperature in a thermocouple type cylinder head temperature indicator is produced by current then, generated by the temperature difference between dissimilar hot and cold junctions. And here's a case where you have the hot junction sensing the temperature there in a cylinder head temperature indicator. So they're going to say, okay, what determines the voltage output and therefore the current of a thermocouple type system? And it's determined by the temperature difference between the two ends of the thermocouple. You guys have got this nailed. Now, where would the hot junction be located once again for a cylinder head temperature indicating system? Well, the hot junction typically would be located right at the hottest cylinder, and the cold junction be located in the instrument. So you guys are getting the questions nailed on this. And let's assume that you decide to use this thermocouple system for a different use. Can you do that? And the answer is no. Thermocouple leads are designed for a specific installation and may not be altered. You can't change the length of the wire. You can't change the use of it from one airplane to another because you're going to get different readings. Now they're going to say, all right, super mechanic, let's assume you get the leads crossed on a thermocouple system. Let's assume you just get them crossed at installation. What's going to happen? Well, if you hook them up backwards, get them crossed, the cylinder temperature gauge would move off scale on the zero side of the meter. It's just trying to read the other direction, that's all. And that tells you then you have the leads crossed, and that's what they're going to ask you about this on the test. Now, where do you normally put the thermocouple for a cylinder temperature system? And the answer is on the hottest cylinder, because you want to measure the worst case situation. Now let's assume you're on the ground with an airplane and you want to measure the fuel-air ratio being burned. How would you do that? The answer is you'd use an exhaust gas analyzer, and it indicates the fuel-air ratio being burned. And the way it works is you stick a probe actually in the exhaust pipe of the engine, and it measures the nitrous oxides coming out, the carbon monoxide coming out, and that tells you the fuel-air ratio. You do that with an exhaust gas analyzer while the airplane's on the ground. Now let's take a look at a question they ask you about engine control systems. They're going to say, let's assume, super mechanic, you're inspecting the engine control systems and you have actually push-pull rods are used in there, and they're going to say, with these push-pull rods, how do you know that you don't have a problem? Well, one of the things you want to look for is look through the inspection holes provided and check the threaded rod ends and to make sure that you have proper thread engagement. And that's a question they ask you on the test about inspecting engine control systems. All right, super mechanic, let you and I talk about valves. Let's talk about things they're going to ask you about valves. And here we have a good example of valves on an engine with lifters and so on. They're going to say, let's assume you're checking compression with a differential pressure tester. And can you do it then? The question they're going to ask you is, can you do it with the cylinder at bottom dead center? What kind of reading would you get? The answer is you wouldn't get any reading at all. And the reason you wouldn't get any reading at all is that when the cylinder's the piston's at bottom dead center, the exhaust valve is open. At least one valve will be open. And so the test cannot be made with the piston at bottom dead center. How about that? All right, how often, they ask on the test, should cylinder compression be checked? And the answer is, on a 100-hour inspection at least, you must check cylinder compression, maybe more often if you think you have a problem. You say, all right, let's assume you're pulling a propeller through and you hear a hissing sound from the exhaust stacks. What does that mean? Well, if you hear a hissing sound from the exhaust stacks, that probably indicates exhaust valve blow-by. Now, what does the clearance between the rocker arm and the valve tip affect? Okay, here you have the rocker arm here and the valve tip. What does the clearance at that point affect? Well, they want you to know it's pretty doggone important because it affects the point at which the valve opens, because it affects the timing, it affects the height of the valve opening, in other words, how much the valve opens, and the duration of valve opening, how long that valve is open. So if you have adjustable valves, they want you to know the clearance between the rocker arm and the valve tip is very, very important. That's the whole idea of that. Now, let you and I take a look at a radial engine. They love to ask you questions on the test about radial engines. So let you and I take a look at the cam ring on a radial engine. And here we have a cam ring on a radial engine. If you remember, this cam ring rotates around. It's these lobes that push up the rocker arm and open the valve. Now, the thing that you need to know is that very often these cam rings are what is known as floating cam rings. By that, there is a lot of play, and these cam rings can float around on their bearing. It's amazing, but that's really the way it is. What holds them in place if they float around in a bearing? And the answer is the spring tension on these push rods holds the cam ring in place. Now, the point they want to make is if you are adjusting the valves in a radial engine with a floating cam ring, this cam ring can float around. How do you do it to make sure that you are standardized, make sure you have the proper valve clearance? And the answer is you've got to make sure that the cam ring is tight against its bearing. You do that by taking this tension off the other side, make sure the cam ring is tight at the bearing, then adjust the valves, and that way you make sure you have the proper clearance. Let me put this exactly the way the FAA does on the test. When adjusting the valves with a floating cam ring, eliminate cam bearing clearance when making valve adjustments. Right there, eliminate cam bearing clearance when making valve adjustments. Now let's assume that you adjust the valves on an engine and you have too much clearance. Well, that's a bad thing because there'll be too much play in the valves, and what's going to happen is you have to take up that play before anything happens. So that's going to result in the valves opening late and closing early. And that tells you right then that the valve isn't going to be open as much, so it's going to cause the duration of valve opening to decrease. It's going to happen for both the intake and exhaust valves. So the valves are going to be open less, and therefore they're going to be closed more. So the valves will remain closed longer than maybe specified by the engine manufacturer. And it's going to reduce the overlap period, because the overlap period is that period during which both valves are open. And if they're going to be open less, it's going to reduce the valve overlap period. So excessive clearance in the valves is a bad thing. There's too much play there, and they're not going to be open enough, and they're going to be closed too long. And that's what you need to know about it. Now let's take a look at some operating principles of a radial engine. And one of the things they want you to know on a radial engine, and this will surprise you, is that when the engine is warm and you have operating valve clearance, the operating valve clearance is greater than when the engine is cold. Now, why is the operating valve clearance, that's when the engine is warm, greater than when the engine is cold? And the reason for that is that the aluminum cylinder expands, pulling the cylinder and the top of the cylinder away from the cam ring, and the aluminum cylinder expands more than the steel push rod does. So when the engine is warm, the operating valve clearance is actually greater than when the engine is cold. So if you use the hot clearance to set the valves, but the engine is cold, what's going to happen? And the answer is the valves will be misadjusted. They will open late and close early because you've got too much valve clearance. So when the engine is cold, you cannot use the hot clearance to set the valves. Now, what happens? Now, we've been talking about excessive valve clearance. What happens if you have inadequate valve clearance? And the answer is if you have inadequate valve clearance, you'll have exactly the opposite. The valves then will tend to not seat positively because the valve tends to be open all the time, and during start and warm up particularly, the valves won't seat properly. So if you have inadequate valve clearance, you'd have a tendency to have the valves open too much, and particularly during start and engine warm up. Now, they're going to say, let's assume you have worn valve guides, and that's basically in here, the valve guide area. Normally you'll have an area that the valve goes through here called the valve guides. If they're worn, could that cause high oil consumption? The answer is yes. High oil consumption is the best indicator of worn valve guides. Now, you could also have other problems causing high oil consumption, but on a test they want you to know that that's the best indicator of worn valve guides. You know, the exhaust valves in an engine take a real beating. They're where the action is. They're where the heat is. There's a lot of hot air going out around those things, and also just a lot of up and down movement, so they really take a beating. So if you're going to overhaul an engine, the odds are in reality, in real life, you're just going to replace the exhaust valve. You're not going to mess around with it. So therefore, the FAA asks you a question about this that is not real life. That's the way things go, folks. This is an FAA written exam. So they're going to ask you, let's assume you're overhauling an engine, and you want to check to see if there's problems with this exhaust valve. Well, a couple problems you can have with the exhaust valve is that it can change its shape and it can stretch. Now, how do you measure for this? Well, exhaust valve stretch can be checked by using what is known as a gauge that looks like this, a contour or radius gauge. And it's this gauge right here, and it's matched to the intended shape of the valve, and you see if the valve has its intended shape, and if it does, you're okay. So you'd find out if you had this stretch by visually comparing the curvature between the neck and the head of the valve and this contour gauge. It's generally supplied by the manufacturer. It's also called a radius gauge. Now, another method you could use to check for stretch is you could measure a reduced stem diameter. If it stretched out, the stem got thinner, and therefore it would tell you that the valve had stretched, and you do that near the neck. Now, here is something that is surprising. Here is a way that is not acceptable to tell if a valve has stretched. And that way that is not acceptable is to measure the length of it. Now, we know that's the correct answer, that you're not allowed to measure the length of it. We've checked with several shops. They say, well, could you measure the length? They say, oh, no, you can't do that. And then we ask them why, and we don't know. It's just not an approved procedure to measure the length of a valve. So if you want to know if a valve has stretched, you use a contour or the same gauge with another name, the radius gauge. Now, let's assume that you decide to grind the valves and you grind them down. What you want to do is grind them down to a beveled edge, not a feather edge. What in Sam Hill is a feather edge? That's the FAA's term for a very thin edge. This is a feather edge. This is a beveled edge. You do not want a feathered edge because a feather edge can get very, very hot. It retains heat. It's exposed to the exhaust gases, not much metal there to protect it, and that can result in pre-ignition and burn valves. So avoid that feather edge. All right, let's talk about oil. Oil is pretty important, you know that. So let's assume that you're overhauling an engine with a dry sump. By the way, a typical engine with a dry sump might be a radial engine, could have a dry sump. The FAA wants you to know before you run this engine, it'd be a good idea to do what is known as pre-oil that engine. So you should pre-oil the engine. How do you pre-oil the engine? Well, you take the oil lines and pump oil into the engine to make sure that you have oil all throughout the engine. Now, how do you know that you have the engine sufficiently pre-oiled? Well, oil will come back from the engine return or the oil pressure gauge indicator port. Now, the return line or the indicator port are the last places generally oil would get to. And if you've got oil to one of those two places, you have the engine sufficiently pre-oiled. Now, let's assume you have been working on an engine, you shut it down, and let it sit for more than about 30 minutes. Now, we're talking about a radial engine here, and that's particularly important. They say, what should you do? Well, you should always turn the propeller through 3 or 4 revolutions to check for what is known as liquid lock or hydraulic lock. And what happens is these bottom cylinders can fill full of oil or fuel, and you know that liquids are incompressible. So if you try and start the engine with the fuel down there, you can actually blow the cylinder off the engine, generally thought to be a bad thing. All right, let's assume that you're operating a cold engine. If the oil pressure of the cold engine is higher than at normal operating indications or normal operating temperatures, what does that mean? Well, what they want you to know, it's normal. for an engine to have high oil pressure when it's cold. That means the engine's lubrication system is probably operating normally. Now, of course, as a mechanic, when you change the oil in an engine, you want to examine the oil, check the oil screen to make sure that there's no metal particles in the oil screen. How could you get metal particles in the oil screen? Well, one way is you have coated surfaces. For instance, we have a cylinder here. It's coated with chrome. If you have defective plating or excessive loads, metal can flake off. The breaking loose of small pieces of metal from coated surfaces is called flaking, and that flaking could cause particles in the oil screen. Now, as you know, it's always good practice when you're changing an oil filter to take that oil filter apart by sawing it through the middle and inspecting the paper element and see what's in there. Now, let's assume you've done that and you find metallic particles. Now, the question is, what are you going to do if you find these metallic particles in the oil filter during an engine inspection? And the answer is you should identify the cause and correct it before the aircraft is released for flight, because it is a big deal if metal particles are found inside the oil filter. Now, let's assume you check the oil filter and you find a deposit of small, bright metallic particles, but they're not magnetic. They don't cling to the magnetic drain plug. You could discover this in the oil sump or maybe on the oil filter, but they're not magnetic particles. What does it mean if they're not magnetic? Well, it tells you that it's not iron. So where could you get this? Well, it could be the result of abnormal plane-type bearing wear. Here's plane-type bearings over here. And if you have abnormal plane-type bearing wear, they are normally, of course, not made out of iron. And, of course, that kind of metal in there would be cause for further investigation. Let's talk about cleaning engine parts. And the thing you want to be careful of when you clean engine parts is you want to watch what you clean engine parts with. One of the problems is if you clean engine parts with the wrong thing, then it creates problems when you reassemble that engine. It can cause oil contamination and foaming and those kinds of things. So when you're cleaning engine parts, including aluminum and magnesium engine parts that they're going to ask you about on the test, it is advisable to avoid soaking them in solutions containing soap. So the answer is no soap. And the reason is soap may become impregnated in the little pores in the metal, and cause engine oil contamination and foaming. So soap can cause engine oil contamination and foaming. Now, what else can you do wrong when you're cleaning engine parts? You can do a lot of things wrong, but one of the things you can do wrong is using water-mixed degreasers. During overhaul, the disassembled parts of an engine are usually degreased with some form of mineral spirits rather than water-mixed degreasers, primarily because the water-mixed degreasers residues may cause engine oil contamination in the overhauled engine. So avoid soap and avoid water-mixed degreasers. Now let's talk about cylinders and pistons again. You guys have been asked a lot of questions about cylinders and pistons. They're going to say, what is the definition of a top overhaul? What does a top overhaul mean? Well, a top overhaul means reconditioning of the cylinders, pistons, and valve operating mechanism. That's it right there. Test question right there for you. Now they're also going to ask you about cam ground pistons. Being the super mechanic you are, I'm sure you know a lot about cam ground pistons. But just in case you don't, let's talk about them. First of all, you would think pistons are round. Well, a cam ground piston is ground so that it's got an oblong shape. Why would they do something like that? Well, the reason you do something like that is on pistons with skirts that hang down on one part but not on another part, the skirts cause the piston to heat and cool unevenly. So when the piston gets to operating temperature, if it's cam ground and has skirts, it now will be round. And so the reason you have cam ground pistons is to provide a better fit at operating temperatures because it becomes round at operating temperatures. All right, during the major overhaul of an engine, they say you should check proper end gap clearance on piston rings. And the way you should do that is you want to make sure that piston rings fit inside the cylinder and leave the proper gap at the end of the piston rings. How do you do that? And the answer is you take the piston ring off of the piston and put it in the cylinder by itself, maybe on top of the piston, and then measure the end gap with a feeler gauge. You put the ring in the cylinder without the piston being there and measure the gap with a feeler gauge. Now let's assume you're putting an engine together and you want to make sure that you have a proper match of piston and particularly the rings to the cylinders of the engine. Well, it's a good thing that you're thinking about this, because you can save yourself a tremendous amount of trouble by thinking in advance about it. Because you cannot use a hardened ring on a hardened cylinder. For instance, you would not want to use a chrome ring on a chrome cylinder, and the reason is you're going to wear that airplane out in nothing flat. So if you do have, we'll say, a cylinder that is either nitrided or chrome plated, these are hardened cylinders, then you would only want to use cast iron piston rings. On the other hand, if you have a plain steel cylinder, you could then use chrome plated rings. But the important thing you want to know is never use a hardened ring on a hardened cylinder, or you could wear that sucker out in nothing flat. All right, now let's talk about the tolerances allowed in aircraft cylinders. Now, car cylinders can go oversized up to 100 thousandths of an inch, but airplane cylinders cannot go oversized that much. Why? Because the walls between the cylinders are very thin, and another reason is that they sometimes are nitrided. You don't want to take away the nitriding. So aircraft cylinders oversized range only from 10 thousandths of an inch to 30 thousandths of an inch, whereas a car could be much more than that. And they want you to know the 10 thousandths to 30 thousandths of an inch on the test. Now, if a cylinder is to be removed, they want you to know you should place the piston at top dead center before you remove the cylinder. Just one of the rules they want you to know about. All right, once again, let's you and I go back to a differential pressure tester. And you're doing a compression check. And let's assume you do a compression check, and the propeller moves in the direction of rotation when you put pressure in the cylinder. What does that mean? That means the piston was positioned past top dead center. You should have the piston at top dead center. If it's past top dead center, it's going to rotate the whole engine around when you put pressure on it. Now let's assume you're doing a differential compression check just like this here, and you hear air coming from the crankcase breather or the oil filler. What's that a sign of? Well, let's take a look at it. If you hear air coming from the crankcase breather or the oil filler, it's a sign of piston ring leakage. Just an example of a piston ring leakage situation, tough situation there. Now let's you and I talk about crankshafts. Now the FAA wants you to know if you're examining a crankshaft and inspecting it, you should use extreme care in checking for straightness. And they call that run out. If the crankshaft, if you hold it at the ends and rotate it around, the crankshaft kind of wobbles as you do that. It has run out, they call that, and there's tolerances for it. Where do you find the run out tolerances for a crankshaft? And the answer is the manufacturer tells you. The current manufacturer's maintenance manual tells you what the run-out tolerances are, or with the manufacturer's instructions for continued airworthiness. So it's a manufacturer that tells you the run-out tolerances on a crankshaft. How do you measure the run-out tolerances on a crankshaft? Well, you do exactly what I said. You put it on a table and rotate it around, and you have what they call a surface plate that contacts the crankshaft, and if it wobbles, the wobble will show up on a dial. So they call it a surface plate and dial indicator, and it's used to measure the shaft run-out. And if it total indication then exceeds the manufacturer's limits, then you have to replace the crankshaft. So when do you check a crankshaft for run out? Well, during engine overhaul or sudden stoppage of the engine. So anytime you have sudden propeller stoppage, you should check for crankshaft run out. Now they say, can you straighten the crankshaft? Well, not if it's a nitrided crankshaft. They don't want you to straighten nitrided crankshafts because they've been hardened and they don't accept straightening well. They have a question. They say, let's assume that you have tolerances that look like this. Let's assume you have that plate move and the dial indicator shows plus 2 thousandths of an inch and minus 3 thousandths of an inch. What is the total crankshaft run out? Well, the total run out would be 5 thousandths of an inch. Now, it's kind of a silly question, but they want you to know you add together the run out in each direction for a total crankshaft run out. All right, let's talk about bearings. Now, the question is, when you as a mechanic are inspecting bearings, what are you looking for? And the answer is, one of the things you're looking for on ball bearings is flaking or pitting of the races, little pieces of metal coming out or little indentations of the races. All right. They also ask you, if you do have indentations on the bearings themselves caused by high static load, what would that be called? And the answer is brinelling, B-R-I-N-E-L-L-I-N-G. That is not a word I use a lot, but that's what indentations on bearings from static loads is called brinelling. Now they're going to ask you, how do you tell when you have a failed or failing bearing? What's the least likely indication? Well, the least likely indication would be low oil temperature, because high oil temperature is an indication of a failed or failing engine bearing. Other things that might indicate a failed engine bearing are low oil pressure and excessive oil consumption. Those are the things that are an indication of a failed engine bearing. Now let's assume you're inspecting either ball or roller bearings. Here we have a ball bearing at engine overhaul, and the bearing checks out fine. No defects at all, except for one little detail. It's magnetized. It's got magnetism. Now, what are you going to do about that? Is that a bad deal? Well, yeah, it's a bad deal because it's going to attract every iron filing that's around, and that is a bad deal. You don't want to attract iron filings in your bearings. So what should be done? Well, that bearing should be degaussed. That means you've gotten rid of the magnetism. Now, eventually, every mechanic has to face a problem of trying to figure out what's wrong with an airplane and doing a little bit of troubleshooting. So as you might guess, they're going to ask you on the test some questions about troubleshooting. First of all, they're going to ask you, what's the purpose of doing a power check? Why would you ever run up an aircraft engine, or particularly a reciprocating engine? And the reason is to determine satisfactory performance. You do not have to be a rocket scientist to be able to answer that particular question. I don't know why they ask it, but the reason you do a power check is to determine satisfactory performance. Now, how could you determine if you had a generally weak engine condition? Well, a generally weak engine condition, when you're operating an airplane with a fixed pitch propeller, or if you have a test club on it, would be indicated by a lower than normal static RPM at full throttle. In other words, if you can't get the RPM at full throttle, then that's a weak engine condition with a fixed pitch prop or a test club. Now, if you are having a very, very unlucky day and you do a compression check, a differential compression check on a cylinder, if all of the piston rings are aligned, if all the gaps are all aligned up so that the gaps are all in the same place, what's going to happen is you're going to have the same indication as if you had worn or defective piston rings, and it would be a false indication. So if all the piston rings are aligned so that the gaps are all lined up, you're having a very bad day. You're going to get a false result of a weak or defective cylinder. Now, let's assume you're doing a ground check and the engine is running rough, and the magneto drop is normal and the manifold pressure is higher than normal for an engine RPM. What's likely the problem? Well, the problem is you have an entirely dead cylinder. So you have that situation. The engine misses in both the left and right positions of the magneto switch. How do you find the dead cylinder? And the answer is go around and feel, very carefully feel, and check for cold cylinders, because that's going to be the dead cylinder. Now, if a reciprocating engine is operated at high power settings before it's warmed up, they want you, Mr. Super Mechanic, to know what's going to happen. And the answer is you might have oil starvation of bearings and other parts. You might, in fact, ruin that engine by operating at high power before it's warmed up. Now, another thing they want you to know about is if you have an excessively rich mixture, what's it likely to cause? And the answer is after firing, because you have deposits in there that retain heat and can cause the engine to fire even though you don't have spark on it. And so if you have an excessively rich mixture, one of the things it can cause is what is known as after firing of an aircraft engine. Now let's talk about something really magnificent. Let's talk about gas turbine engines. And here is a magnificent example of a gas turbine engine. It's a CJ610 on a Learjet. It converts about 200 gallons an hour of fuel into sheer noise, but boy, oh boy, does it also convert it into power. And it's a lot of fun. And they're just wonderful engines. They're smooth, they're reliable, they never miss. If they weren't expensive, they would just be magnificent. Now, these gas turbine engines have a lot of rotating parts in them called rotables. Now, do they last forever? No, they don't last forever. They have limitations. Where would you go to find out the limitations of the rotating parts in a gas turbine engine? And the answer is you'd go to the engine manufacturer's maintenance manual. It provides time and or cycle limitations for those parts in a gas turbine engine. In fact, when it comes to gas turbine engines, the manufacturers pretty much rule everything. They establish the recommended operating time between overhauls, that's called the TBO, and the replacement times for engine parts, and all of that is determined by the manufacturers. Components of turbine engines, replacement times for those, and so on. All right, let's take a look at the recommended operating time between overhaul. Who determines that? Once again, it's the engine manufacturer. Now let's assume, there you go, engine manufacturer, I knew we'd get it. Let's assume you're removing a turbine engine for test cell operation. You're going to take this engine off and put it on a test cell. How do you do it? The answer is according to the manufacturer's instructions. And so you can say manufacturer's instructions for almost all of these questions and get them right through here. Now let's assume you're doing routine maintenance of a turbine engine combustion chamber, and it's a can-type combustion chamber. How is it removed? Well, if you have a can-type combustion chamber, you remove it as a unit. Now let's take a look at hot and cold sections. What do we mean by hot and cold sections? Well, those are the main sections of a turbine engine for inspection purposes. So if you're inspecting this engine, you'll inspect both the hot and cold sections, and that's the way you break them down and think about them. So you and I talk about turbine engine instruments. The primary purpose of a tachometer on a turbine engine. Well, tachometer tells you how fast it rotates. Why do you care how fast the engine is rotating? Well, you want to use that for starting information. You have to know when to bring fuel into the engine for starting, and also to indicate overspeed conditions. So they're going to ask you, why do you use a tachometer on a turbine engine? And that is to monitor engine RPM during starting and to indicate overspeed conditions. By the way, turbine engine tachometers are usually calibrated in % of engine RPM instead of absolute RPM. Just makes it easier to understand. How do you know what the RPM is with a tachometer? Well, once again, it's a three-phase AC generator, sends information to the tachometer and indicator. It's just like the piston tachometer. It's a three-phase AC generator that measures RPM in the engine. Exhaust gas temperature, what's it used for in a turbine engine? Well, it provides a relative indication of the turbine inlet temperature. That makes sense. It gives you, even though you might be measuring exhaust gas coming out the very back, it gives you a relative or comparative indication of the turbine inlet temperature, and that's really what you're interested in. So EGT is kind of an approximation of turbine inlet temperature. All right, there's also a turbine discharge pressure indicator sensor on a turbine engine, and that's normally on a pure jet engine. At the aft part of a pure jet engine, you have a pressure sensor back there, and it's located immediately aft of the last turbine stage. So where would the pressure sensor be for instance, EPR, the aft one? Immediately after the last turbine stage. They're going to ask you, how do you measure turbojet engine temperatures? Well, they are very high temperatures. The answer is you normally use a thermocouple, and because thermocouples, as you remember, don't require an extra source of power, they generate their own electrical power. But what kind of thermocouple? Because it takes a special kind of thermocouple to stand that very high heat, and the answer is a Cromel-Alumel thermocouple, and you need to remember that for the test. Turbine engines normally use a Cromel/Alumel thermocouple because that stands the high temperatures involved. You know, when an airliner like this Boeing 737 gets done with a trip, it's going to taxi into the gate and park for a while they unload passengers and put on new passengers and clean the aircraft and so on. And during that time period, you would still like to have the aircraft air conditioned. So you need bleed air for that. You're going to need bleed air to restart the main engines. You need electrical power when you're doing that. And you could supply all of those services to this aircraft by just keeping one of the main engines running. But that's not a good deal. A much more efficient way to do it would be have an auxiliary power unit. For short, they call that an APU. And an APU is a little turbo shaft engine that you can keep running. It's normally in between the main wheels or back in the tail cone of the aircraft. And that APU can supply compressed air and electrical power for the aircraft. And it's a very neat way of providing those services, much more efficient than keeping a main engine running. Let's take a look at an APU. Here is an APU. You have a compressor section of the engine. These will be axial compressors here, and here's a centrifugal compressor. And that's all driven by the high-pressure turbine, which is over here. And you can see that this would be the gas generator section of the APU. Over here is the free turbine section of it. So you have the low-pressure turbine here and a second shaft that drives the load compressor. So here's the load compressor at this particular point, and it's the load compressor that supplies bleed air for pneumatic systems. So you have this load compressor, and it'll supply bleed air for pneumatic systems. At the same time, this shaft is connected to a generator, and very often that generator is identical to one of the engine-driven generators, and it supplies electrical power where the aircraft's on the ground. Now, for the APU to work best, you need to have a smooth flow of air to the inlet of the APU, and one way you can ensure that is with what is known as a plenum. Now, an air inlet plenum is just an enlargement or a wide spot in the duct, and it allows the air pressure to stabilize before it enters the compressor. So the purpose of this air inlet plenum, that's a wide spot in the duct, is to stabilize the air pressure before it enters the compressor. They're going to ask you about that on the test. Now, let's go back to this APU and talk about it. First of all, you might wonder, the APU is used, they use the bleed air from the APU to start the main engines. How do you start the APU? And the answer is you use an electric starter. An electric starter normally is what's used. It rotates the APU during the start. And remember, the APU is a smaller, much smaller engine than a main engine, so you can do it without pulling that much electrical power. You have a battery for it. Now, where does the APU get its fuel? I can hear you thinking, and the answer is fuel is normally supplied to an APU from the airplane's main fuel tanks. And during the start of an APU, you'd like everything to be automatic as possible, and also during the loads coming on and off the APU, so they do it. The fuel scheduling to an APU is absolutely automatic. It's maintained automatically by the APU fuel control system, and that's during the start, when you change the pneumatic bleeds and the electrical loads. All of that is done automatically with the APU fuel control system. They want to make this just as idiot-proof as they possibly can. Now, another thing that's important about an APU is you want the speed of the generator to be as constant as possible, so you want at least this second free gas turbine portion of the APU running at a constant speed as much as possible. So the speed of the APU when it's in operation is designed to remain at or near rated speed regardless of the load conditions. So when you put a load on it, you're going to have to compensate some way. You might say, well, what's the biggest way you can put a load on an APU? Well, usually most of the load placed on an APU occurs when the bleed air valve is open. You're putting more air through here, and the bleed air valve is normally open when you're trying to start one of the main engines, and you're really working this compressor and putting a lot of load on the APU at that time. So now what you want to do is still maintain a constant speed because you're running the generator. So how do you regulate this? Well, you can do it several ways. You can regulate the fuel to it, but you can also regulate the pneumatic loading on the APU. Now, you might say, how do you regulate the pneumatic loading on the APU? Let's assume you have a change in the electrical load. How can you regulate the pneumatic load? Well, they do that with inlet guide vanes to this load compressor, and you can change the amount of air that gets to the compressor. Now, you might think to yourself, wait a minute, if you have less air getting to the compressor, wouldn't that put more load on this compressor? And the answer is no, it put less load on the compressor. If you actually change these guide vanes so that less air gets to the compressor, there'll be less load on it. That's how you regulate the air getting into the compressor. You don't believe that? Let me prove it. I have here my handy-dandy dustbuster. I'm going to run this dustbuster, and I'm going to give less air to the dustbuster, and let's listen to see what happens to the RPM. Here is the normal RPM. It takes a while to build up here. Normal RPM, I block the inlet, and RPM increases. I open the inlet, RPM decreases. Why is that? Because when you open the inlet, you have more air impinging on the compressor, and that puts more load on the compressor. When you close the inlets or restrict the air getting to the compressor, then there is less air getting to the compressor. It's thinner air anyway, and the compressor has less load on it. So you can change the pneumatic load, and you can change the electrical load, and you can change the fuel. And you do all of that, change the pneumatic load, the electrical load, and the fuel to maintain a constant RPM and a safe EGT. So generally, when the maximum APU shaft output power is being used, and at the same time you're using pneumatic power, the pneumatic power is automatically modulated to maintain a safe EGT so you don't overtemp the EGT on the engine. Now, finally, the last thing you need to know about APU operation, it's all automatic. Everything works just smoothly and easily with very little attention from the pilots, but you do need to cool it down before you shut it down, and you can do that by closing the greatest source of load for the APU, and that's the bleed air valve. So before you shut it down, what you need to do is cool it down by closing the bleed air valve for a while. Now, let you and I talk about starting a turbine engine. Maybe this is one that's already started here, I don't know. But they ask you the proper sequence for starting the engine. Well, first of all, you want to get the engine spinning. You do that with the starter motor. Then you want to make sure that you have ignition to the engine. And the very last thing you do is supply fuel to the engine. The reason the fuel is the last is you want to make sure that you have everything else going. Proper air, ignition, then the fuel. That way you're avoiding a hot start. Now, what is a hot start? Well, a hot start is if you have exhaust gas temperature go too high. How do you tell when you've started an engine? Well, the first indication of starting an engine is you have a rise in the ITT or exhaust gas temperature, either one. So a successful start is indicated by the rise in the ITT. If the ITT or exhaust gas temperature goes too far, then you have a hot start, and a hot start is indicated, according to the FAA, if exhaust gas temperature exceeds specified limits, then that's a hot start. Now, what is a hung start? Well, a hung start occurs when the engine fails to reach idle RPM. Now, a general cause of a hung start is the starter cuts out too early, and if the starter disengages too early, then the engine might not reach idle RPM. It'll just stay right there and stay there and not get there. So the starter should not be either disengaged manually or disengage itself until you get to idle RPM. What do you do if a turbine engine catches fire during starting? Well, run might not be the correct answer on the test, but you turn off the fuel and continued cranking, because what you want to do is keep air coming through that engine. So turn off the fuel and continue cranking if you have a fire. Let's talk about the air inlet in the compression section of a turbine engine, and we'll lead off by talking about an air inlet, and that is an air inlet. If there ever was one, that is an air inlet. That is a big one. And that engine is pulling in a tremendous amount of air. In fact, they're going to ask you a question: what's the air pressure within this inlet of a turbine engine being operated while it's in place on the ground? Is it positive or negative? And the answer is it is negative, due to high velocity of airflow being taken into that engine. And so therefore you have very low air pressure here, and they call that negative. It's less than ambient due to that high velocity airflow. So a lot of air going into the engine. Sometimes you can see the effects of all of this air going into the front of this engine here, because when the engine's near the ground, sometimes you can get a little miniature tornado or dust devil called a vortex. And it's just rotating air that creates a vortex, just like a bathroom drain vortex, but it's going up into this engine. And that vortex can be a very bad thing, because it can lift gravel and rocks and dirt and even nuts and bolts and direct them right into the engine. So you want to get rid of that vortex, and sometimes they do that with a blast of air in front of the engine to break up that vortex, and that blast of air is called a vortex dissipator. So these are vortex dissipators, and are installed on some aircraft with the wing pod installed engines that are real close to the ground with low ground clearance. And the idea is to prevent FOD, foreign object damage. They use a stream of engine bleed air blown down towards the ground ahead of the engine. And they're generally activated, these vortex dissipators are generally activated by a landing gear switch or a squat switch. And so when the engine is operating and the weight of the aircraft is on the main gear, these vortex dissipators will be blowing air in front of the aircraft to break up that vortex so you don't get FOD damage inside the aircraft. Now, getting the air inside an engine is sometimes a very difficult proposition. Here's an aircraft that cannot count on ram air. Helicopters move very slowly. And if you can't count on ram air, the best inlet shape is what is known as a bell mouth inlet. It looks like a bell. Here we have a guard to prevent ice from getting in the engine, but if you looked at this inlet itself, you'd see it was shaped like a bell, and that's called a bell mouth inlet. The purpose of a bell mouth compressor inlet is to maximize the aerodynamic efficiency of the inlet when you do not have ram air pressure forcing the air in. Now, another problem that you have is FOD that we talked about earlier. You can get FOD when the engines are mounted near the ground. Turboprop engines very often have FOD problems, so they install the engine with a bend in the airflow going into the engine. Helicopter engines, they have the same thing, and that is what is known as a particle separator. Particle separators separate sand and ice and give clean air to the engine, and they function by utilizing a sharp airflow directional change or bend to take advantage of inertia or centrifugal force, and that filters the air to the engine. And sometimes they also have air filters and inlet screens, but particle separators are a very big way of making sure you don't get FOD in these turboprop engines. Right at the front of a lot of gas turbine engines is the fan. And as you can see, these fan blades are held apart a certain distance from each other by these shrouds here that go in between the blades. Well, if you have an engine overspeed or foreign object damage, these fan blades can move out of position. In order to do that, these shrouds will have to overlap, and the blades themselves can overlap a little bit. And that condition is called fan blade shingling, and it's caused by engine overspeed or by foreign object damage, and it's a bad thing. You'd have to, of course, inspect that engine very carefully. Now let's move a little further back in that engine and take a look at the compressor section of the engine. And of course, the whole idea of the compressor section is as the air moves aft in the engine, you increase the air pressure before you go into the burner can. Now there are two types of compressors you can have. Here's an axial compressor. This section is the axial part that moves the air along the shaft or the axle of the engine right straight back. And here's the centrifugal compressor that shoves the air outside, slings it to the outside of the engine, thereby increasing the pressure of the air. So these are the two types of compressor blades. They do increase the air pressure in the engine before the air enters the burner can. And one of the things you have about axial compressors, if you look at these blades very, very carefully, you'll notice that these blades are each individual little airfoils. And they work on the principle of any airfoils. They have an angle of attack, and their efficiency is dependent on a smooth flow of air over those airfoils. Now, you could actually have these compressor blades stall. And if these compressor blades stall, that is a very bad thing, because now you have a disruption of the airflow in the engine. You have tremendous increase in temperatures inside the engine, and that is not a good thing. So you'll want to avoid compressor blade stall. And you can do that by managing the angle of attack of these individual blades. Well, one way you do it is make your power changes smooth without having rapid RPM changes. And the other thing you can do is fiddle with the air coming into the engine so that you don't have big angles of attack. Or you can actually relieve the load on the compressor by bleeding some air off during low thrust and low RPM conditions. So let's assume that you want to keep this air flowing smoothly in the compressor. One of the things you can do is have variable guide vanes. Now, variable guide vanes adjust the flow of the air going into the compressor to keep it smooth. The other thing you can do is have bleed valves, and bleed valves bleed off some of that compressed air so that you don't make the compressor blades work as hard. And both of these, the variable guide vanes and bleed valves, are used in turbine engines to aid in stabilization of compressor airflow. And what that does is keep that air going smoothly through the engine, particularly important during low-thrust engine operation. Now, let's assume that you have a turbine engine and you're at takeoff EPR, but what you find is you reach the EGT limits. The engine gets too hot before you get the proper thrust. You can't reach takeoff EPR. What would this tell you? Well, it could be an indication that the compressor blades themselves are either contaminated or damaged, because these compressor blades are airfoils and they're dependent on the smooth flow of air over these airfoils. And if the blades are contaminated or damaged, instead of compressing the air, they'll tend to heat the air, and they also might have compressor stall, and that'd be a very bad thing. And therefore, the compressor is less efficient. You know, when you realize how tremendously fast all of these parts are rotating around inside a turbine engine, you realize that anything that gets inside that engine could cause disaster, and that includes any ice. You don't want any ice to go through this engine. So you have an engine inlet anti-ice system, and that's to prevent ice formation in the engine or in the inlet areas of the engine. And anti-ice is not used for ice removal, because if you use it for ice removal, the ice could break off and get through the engine. That'd be a real problem. Now, how does this work? Well, normally anti-icing of jet engine air inlets is commonly accomplished by engine bleed air. You take engine bleed air from the compressor, it's hot, you run it up here to the dome of the engine, the air inlets here in this lip of the engine, and that heats it up, and again, you're talking anti-ice, and you're preventing ice from forming on the engine. Now, when you do apply this anti-ice, you're going to get some change in your engine readings. For instance, your RPM, your exhaust gas temperature, and EPR readings may shift noticeably because you're taking bleed air away from that engine, which would be used for the engine normally to run the compressor, or the compressor uses to run the engine actually, and you're taking that away and you're applying heat to the inlet of the engine, so you're going to get some changes in RPM, EGT, and EPR. You might not notice too much change in the fuel flow, but you will in these parameters, RPM, EGT, and EPR. Sometimes the FAA loves to ask you what-if questions. And a what-if question goes like this in this particular case. You have a jet engine. Let's assume the pilots are flying along. They spot icing conditions out there ahead of them, and they're not going to change anything. They might pull the power back a little, then leave the power levers alone, and they're going to fly at constant power. Now, we're going to have to ask, first of all, what's the definition of constant power? And we think in this particular case, we're saying you don't change the power levers. You keep them the same. And then you turn on anti-ice. Well, what happens to an engine when you turn on anti-ice? You heat the inlet of the engine up, and you have warmer air going into that engine. Now, let me ask you a question. If you have warm air, is that air more or less dense? And the answer is that air is less dense. So you turn on engine anti-ice, you don't change anything else. Is that engine going to produce more or less thrust? And the answer is, well, you got hot air coming into the engine. It's less dense. The engine's working on thin air. You're going to have less thrust. And what gauge do you use to measure thrust? EPIR. So the whole point is, if you're flying along at a constant power setting in an airplane and you turn on engine anti-ice, you will see a noticeable shift in the EPIR reading, and it'll be a shift down because you're operating with less dense air. Now let's assume that you keep the RPM of an axial flow compressor constant. Now here's an axial flow compressor. That's these stages right here, and that's one that moves the air straight back along the shaft or axle. If you keep the RPM constant, could you change the angle of attack of the blades? Well, yeah, you could change the angle of attack of the blades by changing the velocity of the airflow. So two things will have a tendency to change the angle of attack of those compressor blades. Number one is the RPM, but if you keep the RPM constant, you could still have a different angle of attack by changing the velocity of the airflow. Now, you could, if you don't maintain smooth engine operation or you have contaminated blades, you could have compressor blade stall. And compressor stall, as we said earlier, is a bad thing, and it's caused by high angle of attack of the airflow, generally on the first stages of compression here, and these blades would begin to stall here, and that would be a very bad thing. Now, here's a concept they're going to ask you about, and that is if you have two parts rubbed together, what would it be called? And that would be called galling. My mom used to always use that term. That really galls me, and it's the same thing. Things are rubbing together, and it's a severe condition of chafing or fretting, and that's called galling, and it's a transfer of metal from one part to the other. So severe rubbing of turbine engine compressor blades, if you had this in the compressor section, if they rub against the outside, that would be called, it would cause galling. It would be a very, very bad thing. Now, once again, looking at these compressor blades, you want them to be clean, and you don't want them contaminated in any way. Well, if you had dirt particles in the air introduced to the compressor section of the engine and in the inlet guide vanes, then that would contaminate those blades. But they're going to ask you, would it form a coating on the turbine blades? And the answer is no. These turbine blades are really in a high heat environment. It's going to burn off any coating, so you would not have a coating on turbine blades. So dirt particles will form a coating on compressor blades and the casings and inlet guide vanes and the cool section of the engine. But when you get back here in the hot section of the engine, you're not likely to get a coating because you're likely to burn it off. Now, when you do have an accumulation of contaminants in the compressor of a turbojet engine, it does reduce the aerodynamic efficiency of the blades. And what that really means is for any given thrust or EPIR, you're going to have higher EGT. So accumulation of contaminants is a very, very bad thing. You want to get rid of those contaminants. So there are two common methods for removing dirt deposits from turbojet compressor blades. And one of these is a fluid wash, and the other is an abrasive grit blast. I've heard of people talking about walnut shells. I think you would only have to use FAA-approved walnut shells. But those are the two ways to clean compressor blades. It's a fluid wash and an abrasive grit blast. That second one sounds like it could end up being expensive. I don't know. So what do they call this cleaning? They call that field cleaning if you do it out in the field. And it's a procedure for removing the accumulation of dirt deposits on compressor blades, and that's referred to as field cleaning. Now, compressor field cleaning on turbine engines is performed primarily to do these things. It will prevent degraded engine performance, it will prevent increased fuel costs, and it will prevent damage or corrosion to gas path surfaces. So they want you to have the general idea that taking care of those compressor blades and keeping them clean is a very, very important thing. Now, if you have damage to blades and vanes, it's not the end of the world because you can go look up in a book and see what you can do about it. In some cases, depending on where the damage is, you may be able to do a repair, also depending on how much damage you have. And there are different codes outlining sections of the blades and what you can do about it, and they call these coded areas on the test. but a type of repair to turbine engine compressor blade coated areas for each individual area is accomplished by a procedure termed blending. And blending is a hand method of recontouring damaged blades and vanes. And it requires the use of small files, emery cloth, and honing tools. Now, this isn't something you do very lightly. The blending of blades and vanes in a turbine engine should be performed, first of all, parallel to the length of the blade, along the length of the blade, and using smooth contours to minimize stress points, because you don't want to accumulate stress in any individual point. Now let's move a little further back into the engine, and we'll talk about what is known as the hot section of the engine. And I think the reason this is called the hot section is, folks, things really get hot here. Let's take a look at how this works. Of course, first of all, what happens, you have air entering the burner can, it's mixed with fuel, and then the velocity of this now hot gases increases tremendously and rushes out the back. In the meanwhile, it passes through some guide vanes that guide the air into the turbine section, and then, of course, it hits the turbine wheel and spins the turbine wheel. Let's take a close look at those guide vanes and turbine wheel and see what we're talking about here. Any part in an engine that does not rotate is called the stator. The parts that rotate are called the rotor. So the turbine wheel rotates, that's called the rotor, and the stator is these guide vanes that guide the air into the turbine blades. Now, this stator is often called a nozzle because you can see that it comes down here and directs the air like a nozzle does right into the turbine blades. Now, where does the heat take place in an engine? Well, the highest heat-to-metal contact in the jet engine is in these turbine inlet guide vanes. That's what this stator is called, inlet guide vanes, and this is where things are really hot because the burner can was just right over here, so it's the air coming right out of the burner can. Now, the turbine inlet temperature is the most critical engine variable during turbine engine operation, and it's monitored to minimize the possibility of a hot start. So what you're doing is when you're monitoring turbine inlet temperature, you're monitoring the temperature right here, and that's the part where you're most likely to have heat damage in a turbine engine. The hot section of a turbine engine is particularly susceptible to what is known as cracking damage. And cracking damage will come because of a tremendous amount of heat. Of course, the hot section begins when you add fuel to the air in the burner can and you have flame going on. And of course, that really hot air now goes past the turbine blades, and the turbine blades are in the hot section of the aircraft. Once again, the compressor blades up here, you're just compressing the ambient air. It's a little bit warm, but that's not the hot section. It's considered the cold section of the engine. So the question I'm going to ask you about this one more time is, would you expect damage to turbine blades or compressor blades to occur more frequently and be greater in a turbine engine? And the answer is damage to turbine blades is apt to be greater in a turbine engine than damage to compressor blades, because these turbine blades back here are exposed to very high temperatures. Now let's take a look one more time at the nozzle leading to, these vanes represent the stator or nozzle leading to the turbine blades, and they're going to ask you, how about the serviceability limits for turbine blades as compared to nozzle vanes? Well, these are the nozzle vanes. And once again, the turbine blades are rotating. They're not only in a hot section, both of these are in a hot section, but the blades are rotating. They have a lot more stress on them. So serviceability limits for turbine blades are much more stringent than those for the nozzle vanes. And a limited number of small nicks and dents in turbine blades can usually be permitted, but only a limited number in the areas away from the root area. So you have to inspect these turbine blades very carefully for damage. Now let's take a look. Let's assume you want to look inside this engine and see how things are going inside. Well, there are plugs you can take out and stick a borescope in there, and a borescope is basically a fiber optic device that you can actually guide into the engine and look inside of it. You want to know the name of it? That's called a borescope, and you can look inside the engine. So a borescope, according to the FAA, is used to accomplish internal inspection of installed turbine engines. Now, what would happen if you have over temperature conditions? What would it cause? What would cause what they call stress rupture cracks in the leading edge of turbine blades and a possibility of turbine blade failure. So if you get to looking at these turbine blades themselves, you might see a stress rupture crack, and that could cause turbine blade failure. Now, stress rupture cracks appear on turbine blades for turbojet engines across the leading edge to the trailing edge at a right angle to the blade length. So you'd expect to see stress or rupture cracks go in this kind of direction, not that kind of direction. You know, when mechanics have an engine all apart and they're looking at it, they like to talk to each other, and very often you'll see some guy get a pencil out and he wants to mark what he's talking about. Well, the FAA wants you to know that turbine engine components are exposed to very high temperatures, and creating a little pencil mark may create a weakness later on that could cause that part to fail. So these turbine engine components can only be marked during inspection with materials allowed by the manufacturer. And these things include, well, chalk, layout dye, and a felt tip marker. A commercial felt tip marker is often allowed. But you don't want to mark it with just anything. Things that are generally not allowed are wax or a grease pencil or a graphite lead pencil, because you may find that your little bit of marking caused later damage down the road. Now, are cracks in turbine blades acceptable? No, not to any extent. Cracks in turbine blades are not acceptable to any extent. Now, let's assume you get this turbine blade very, very hot and you have a lot of centrifugal force on it. You can see it gets almost kind of plastic. It might tend to grow or creep. Well, creep is not a reference to my personality in any way. Creep is a reference to what is known as permanent and cumulative deformation of the turbine blades. What causes creep? Well, continued and or excessive heat and centrifugal force will cause blade creep. They actually get a little bit longer. Sometimes that's called blade growth. Now, jet engine, turbine engine blades, if they are removed for a detailed inspection, must be put back. Where do you put them back? In the same place you took them away from, in the same slot. And the reason for that is to maintain engine balance. Now, gas welding and straightening of turbine blades, these rotating airfoils they call them in the turbine engine, does require special equipment and is not often recommended by the manufacturer. So don't plan on doing a field welding or straightening of a turbine blade, because it requires special equipment and it is not often recommended by the manufacturer. Fat chance, I think they're trying to tell you right there. Now let's assume you have a turbine engine and you'd like to know how much thrust that engine is putting out. Well, one way you could find that out is you could measure the air pressure at the front of the engine and the air pressure at the rear of the engine and measure the ratio between those two, and that would tell you how much thrust that engine's putting out, and they do that. That's called engine pressure ratio. The other way you could do it is you could measure how fast the fan is turning, because in most fan engines, the fan is putting out most of the power that the engine puts out. So if you know how fast the fan is going, the RPM of the fan, that will tell you how much power or thrust that engine's putting out. So some turbine-powered aircraft use RPM as the primary indicator of thrust produced. Others use EPR as the primary indicator of thrust produced. And basically it depends on whether or not the engine has a fan. Generally, if the engine has a fan, they will use RPM as the primary indication of thrust produced. Now let's assume that you want to know how well the engine is working. Does it have mechanical integrity? Is it putting out power? Well, one of the things you would look at is exhaust gas temperature. And the reason you'd look at exhaust gas temperature, it tells you how much fuel and how much heat there is in the engine for a certain amount of power. So exhaust gas temperature is used to monitor the mechanical integrity of the turbines, as well as to check engine operating conditions of a turbine engine. And high exhaust gas temperature tells you that engine is not doing as well as if it had a cooler exhaust gas temperature. Now let's assume a gas turbine engine has a high exhaust gas temperature. Let's assume it also has high fuel flow and it has low RPM. So high exhaust gas temperature, high fuel flow, low RPM. What would cause that? One thing that could cause that is turbine damage. Something is wrong with the turbine blades, or some other cause of loss of turbine efficiency. Some reason or the other, this turbine section may not be as efficient as it should be. One of the reasons would be turbine damage. Now let's assume that you have a turbine engine with a high exhaust gas temperature for a particular power setting, particular EPR. And let's assume, on the other hand, you check this engine over very carefully. You look at it with borescope, you check it out, and you find out that there is no significant engine damage. So you have a high EGT for a particular EPR, and you can't find any engine damage. Now what would you check for? And one of the things you would check for is the engine out of trim? And that means, is the engine fuel controller not adjusted properly? And that would be the thing to check. Under these circumstances, you trim the fuel controller of the engine. Now, when a turbojet engine indicates no change in power setting parameters, everything's the same, EPR's the same, fan speed is the same, we'll see exhaust gas temperature's the same, but in spite of all of those things being okay, no change in power setting parameters, the oil temperature is high. What would be a cause of that? Well, one possible cause is what the FAA refers to as engine main bearing distress. You might have a bearing failure coming up, and you would know that by the high oil temperature with everything else being okay. Now, let's assume you've just finished a flight or running an engine very hard. One of the things you want to do is make sure that you allow, in some turbine engines, a cooling off period, because you want the turbine case, to shrink at the same rate that the turbine wheel shrinks. Otherwise, if you do not allow the turbine wheel to cool, the case can contract around it, and that is a bad thing. And so, therefore, you should allow a turbine engine cool off period after operating at reasonably high power settings. Now, believe it or not, you and I have covered power plants. So now you're equipped to understand the majesty of this engine and the thrust it produces.